Welcome to Solving Logarithmic Equations. In Math 99, Winter 2017, this is outcome 6C. So we have several tools we will use to solve logarithmic equations. So these are rewrite using the inverse function. This works whenever we have a very basic logarithmic equation, right? The logarithm is the inverse of the exponential function, and so we can always take this basic logarithmic equation, log base b of x equals y, and rewrite it with the same base as an exponential function, b to the y equals x. Another tool that we can use is the one-to-one property. And this one is for a very specific case. If we have the log base b of x equals the log base b of y, then x equals y. So notice that we have just a logarithm, and the bases match. All right, so let's solve some equations. First equation that we are going to solve is the log of negative x equals 1.25. Now we don't have a base written with this logarithm, which means that it's the common log. So this is the log base 10 of negative x equals 1.25. Okay, so we can rewrite it as an exponential function with the base of 10. All right, so our base is 10. And we know that the logarithm is an exponent, so 1.25 is going to be the exponent on our base 10. And that is going to be equal to our argument here, negative x. Now we haven't finished solving for x yet. First we need to multiply both sides by negative 1 to get just x. And so x is equal to negative 10 to the 1.25. Now if I put that into my calculator, negative 10, I get negative 17.7827941. We're being asked for the nearest thousandth, and thousandth is 3 decimal places. And so I'm going to round it to the third decimal place. Got negative 17.7827, so I'll round that 2 up to 3. So x is approximately negative 17.783. All right, so we are done. We have our exact answer and we have our approximate answer. All right, why don't you give this one a try? Solve the log base 3 of x plus 1 equals 2. Our solution is 3 to the second power equals x plus 1. It's a base 3 logarithm, so it's going to be a base 3 exponential equation. 2 is my exponent because the logarithm is an exponent. So 9 is equal to x plus 1. I subtract 1 from both sides, and I get x equals 8. Let's try another one. Here we go. All right, so we're being asked for an exact simplified answer and an approximate answer accurate to 4 decimal places. We're starting with the natural log, and so of course the natural log is the base e logarithm. So when I rewrite that as an exponential equation, e is going to be the base of my exponent. So that's e to the fourth power is equal to 2 minus t. I can subtract 2 from both sides, and now I have negative t equals e to the fourth minus 2. I'm going to need to multiply both sides by negative 1 to get t. And I'm going to just rewrite that in the opposite order. I'm changing both sides. So this is going to be a negative e to the fourth, and this is going to be a positive 2. So I'm going to write it as 2 minus e to the fourth power. So that's my exact simplified answer. My approximate answer we get by putting that into the calculator. So 2 minus e to the fourth, right? I can get e as the second function of my natural log button. So that's how I get, oops, there's natural log button, right? So e to the x is the second function of the natural log button. Okay, so 2 minus e to the fourth is negative 52.59815003. So 4 decimal places, right? So 5, 9, 8, and I'm going to round that 1 up to a 2 because the next digit is 5. All right, so there's my approximate answer. Okay, so all of the problems we've tried so far have involved the first tool that we had, which was rewriting using the inverse function. So we've been doing this. We've been taking a logarithmic equation and we've been changing it into an exponential equation. So now we're going to be looking at one where we will use the one-to-one property. Now there are a couple things we need to check to make sure that we can use the one-to-one property. The first thing we need to make sure is that we have logarithm equals logarithm. Right? I can't have 2 times the logarithm or 1 plus the logarithm. It just has to be a bare logarithm and a bare logarithm. Now they have to have matching bases. So this is a base 2 logarithm. This is a base 2 logarithm. Right? So if both of those things are true, then we are set to use the one-to-one property. And the one-to-one property basically says if the log base 2 of 5x equals the log base 2 of x squared plus 6, then 5x has to equal x squared plus 6. Right? We're able to eliminate the logarithms quite easily here. And this leaves us with a quadratic equation. And so we will solve this quadratic equation the way we always solve quadratic equations. We need to get an equals 0. So I'm going to subtract 5x from both sides. So 0 equals x squared minus 5x plus 6. And at this point I can use the quadratic formula if I like, but I'm going to factor because I know that for me factoring is quicker and it's also less error prone than using the quadratic formula. Now you may have different experiences with factoring in the quadratic formula. And any way you want to find this answer, any algebraic way is fine. All right, so I've factored this into x minus 2 times x minus 3. And now x minus 2 times x minus 3 equals 0. I can use the zero factor property to set each of those factors equal to 0. And so my answers are x equals 2 or x equals 3. All right, so you'll notice that we're being asked to find approximations accurate to the nearest tenth. right? So we're rounding it to 1 decimal place. So rounded to 1 decimal place, 2 is 2.0, and 3 is 3.0. That 0.0 actually has meaning. It tells anyone who looks at it that it is accurate to the tenth. All right, so go ahead and solve this equation, which is kind of similar. All right, so I've checked, and I see that I have a natural log and a natural log. So I have logarithm equals logarithm, and they both have the same base. I can use the one-to-one property here. So 2x plus 3 equals x plus 15. So now I need to solve this equation. Now I don't have a quadratic equation this time, I just have a linear equation. So I'm going to get the x's together and the things that aren't x's together on the other side of the equation. So I'm going to subtract x from both sides and subtract 3 from both sides, and I get x equals 12. That's my exact simplified answer. Okay. So what is going on with this equation? Right? I have 5 plus the log base 2 of x equals 4. If I go to look at my tools for solving, I actually don't have it set up well for either of them. I can't use the one-to-one property because I don't have 2 logarithms, right? So I can, eliminate that right away. So my only tool that I have left is to rewrite it using the inverse function. The log base b of x equals y is equivalent to b to the y equals x. But I don't have just a logarithm here. And so this is a situation where solving using inverse operations comes in. I'm going to isolate this logarithm, and then I'm going to use my rewrite using the inverse function tool. Okay, so the first thing I'm going to do on this equation is I'm going to subtract 5 from both sides. When I subtract 5 from the left, I get the log base 2 of x. When I subtract 5 from the right, I get negative 1. Okay, so now I have a very basic logarithmic equation. I'm going to rewrite it as a base 2 exponential equation. Right? The 2 is the base, the logarithm equals the exponent, and this exponential expression is going to be equal to the argument of my logarithm. So x equals 2 to the negative 1, and 2 to the negative 1 is 1/2. So x equals 1/2 is my answer, my exact answer, and I can round that to the nearest hundredth by writing it as a decimal. So 0.5 would be exact, but since we're asked for something accurate to the nearest hundredth, I will round it to the nearest hundredth, so it's 0.500, so I don't need to round up. All right, give this one a try. As with the previous one, I've got a little bit of work to do before I can rewrite it as an exponential equation. I've got 3 times the natural log of x plus 1 instead of just the natural log of x plus 1. So I'm going to divide both sides by 3 to get the natural log of x plus 1 equals 5/3. So now I've got a logarithm equals something, and I can use my, my tool, my rewrite as an exponential tool, to solve that. Right? So the logarithm is going to be base e, and the logarithm is the exponent on e, so 5/3. E to the 5/3 is going to be my exponential expression, and that's equal to x plus 1. So now I just need to subtract 1 from both sides to get x, and so x is equal to -1 plus e to the 5/3. It's all right to write it as e to the 5/3 minus 1, but this is one of those situations where we usually write it in this order to avoid any confusion, right? It can, if you have some sloppy handwriting, it can be difficult to understand whether the 1 is in the exponent or not. If you write it out front, there's no question. All right, so we also want an approximation accurate to the nearest 10,000th. So 10,000th is 4 decimal places. And we can grab our calculator and put in our answer, -1 plus e raised to the 5/3 power. And we get 4.294490005. And everything's getting rounded up today, but that's just random variation. So 29449, so because the 5th digit is 5 or greater, we're going to round up that last digit 4. So x is approximately 4.2945. Exact answer, approximate answer. All right, we have one last problem, or exercise if you prefer. One last exercise. Before I solve this equation, I want to have a brief discussion about penmanship. Penmanship is incredibly important when you're working with logarithms. This is mainly because a logarithm without a base has a meaning. It's our log base 10. Imagine if this x squared were written a little bit too low. It would be easy to mistake this common log of x squared for a log base x of 2. Make sure when you are working with logarithms that you write your argument, like the x squared, in line with the word log, and make sure that your base is definitely written as a subscript. Now let's solve it. The first thing I'm going to do when solving is I'm going to subtract 9 from both sides. This is going to get the term with the logarithm in it by itself. This is going to give me -2 times the common log of x squared equals -8. Right? I subtracted 9 from both sides. 1 minus 9 being -8, and the 9 disappears from this side. So now I'm going to divide both sides by -2, and that gets the logarithm by itself and 4 on the other side. So now I can rewrite this as an exponential equation. So my base for my logarithm is 10, and so it will be a base 10 exponential equation. 10 is the base of my exponential. The logarithm is an exponent, so that's 10 to the 4th power, and that's equal to x squared. All right, so x squared is equal to 10 to the 4th power, which is 10,000, and I can apply the square root property. to find x. So x has to be either the positive or the negative square root of 10,000, which is 100. So x is equal to 100 or negative 100. Another thing to watch out for when you're solving log equations is that your answer works in the original problem. Now in this case it does. I can plug in 100 or negative 100 and it's going to make this equation true. But do remember that the logarithm only accepts positive numbers. So if your answer would make the argument of the logarithm negative, it's not a good answer. And that's it for solving logarithms. Have a good one.